This video is about function generators. It corresponds to section 6.4 of Applied Analog Electronics. Now, the purpose of a function generator is to produce a periodic signal that has an arbitrary wave shape, arbitrary frequency, arbitrary amplitude, arbitrary DC offset. Now, to get all this arbitrariness, we end up doing most of the work digitally. And let's take a look at the components that go into making an arbitrary function generator. Okay, the first thing we need to know what the waveform is. And that is done by having a lookup table. And it's going to have a number of entries in it, let's say L entries, and each one has got particular precision. They're usually integers that are appropriate for whatever digital analog converter we've got. The output of that table is going to go into a multiplier and get multiplied by the amplitude. So the table is basically between -1 and 1. And then we're going to have an addition of an offset. And this work here, after you come out of the table, the multiplication and the addition can be done either in analog or digital form. And that's a question of where do you put the digital analog converter in this chain. And different function generators are going to pick different solutions for that. There's not an arbitrary, this is the way to do it. There's many different ways, and there's trade-offs, as there is in almost every engineering design question. The way the Analog Discovery 2 does it is it puts the digital to analog conversion here. So it does the multiplication for the amplitude in digital form, but it does the addition of the offset in analog form. And the reason for that is that the digital analog converter they're using has got two different ranges. If you're running plus or minus 5 volts into the digital analog converter, you have a precision of something like 664 microvolts. So that's the step size. But if you can keep the thing down to 1.25 volts, so the amplitude less than 1.25, then you can get a precision of 166 microvolts. So by separating the offset, we can have the high precision on a small analog signal added to a relatively large offset. Okay, all this is well and good, but it only takes care of the output of the table. What goes into this thing? Well, we need to have a number between 0 and L, so something that's basically a subscription to the table, and we do that by having a phase here that's appropriately scaled, so it's in the range 0 to L. And that phase needs to get updated because phase is a time-varying thing. It changes on every tick of the clock. And the way it changes is we're going to just take the phase and add it to the frequency. Now the frequency has to be scaled appropriately so that each tick of the clock increments the phase by the amount that would get us through the table in the appropriate amount of time for one period to correspond to this frequency. But these are just scaling factors that can be taken care of by the software, so that when we're working with it as a user, we specify frequency in hertz. We don't have to worry about how this gets scaled internally. The table length for the Analog Discovery 2 is one of those parameters that actually can be changed, though it requires a little bit of fussing to get to it to change it. The default is 4096, which is 2 to the 12th. And the table lengths are nearly always powers of 2, because in order to keep this phase in this range, we rely on some properties of binary arithmetic so that the word just overflows and we throw away the stuff that gets bigger than L if L is a power of 2. Okay, you need to know the symbol for a function generator in a schematic, and there's a couple different ones, but they're pretty much the same. you'll see a circle. Sometimes you'll see it as a square with the waveform in it and two ports. Function generator generates a voltage. There's always two ports to any function generator. One of them is the positive one, the other one is the negative one, and that's basically saying how we interpret which way up this table is, which way this offset goes. So if we've got an offset of plus 1 volt, that means the positive terminal here is 1 volt relative to this for the DC. If the table has a sudden spike upwards and then a flat spot, it's going to be a positive spike on the positive terminal. The waveform generators that we have on the Analog Discovery 2 only have one wire coming out of them. And that's because they have internally the other terminal hooked up to ground. You have to draw that on the schematic. You can't draw the function generator with just a single terminal. That doesn't make any sense. It's always got two terminals. One of the terminals is internally wired to ground, so draw that connection. Okay. The other symbol you'll sometimes see is a square box rather than a circular one, and sometimes you'll see a word like function generator rather than the sine wave symbol, or sometimes you'll see, if it's an arbitrary waveform generator, you'll see some other sort of squiggle that corresponds to the arbitrary waveform. Okay, so let's take a look at what this looks like with the Analog Discovery 2. Here is the Analog Discovery 2. The yellow wire is waveform generator 1. There are two waveform generators. There's also a yellow one with white stripes, and that's waveform generator 2. The other wire, as I said, has got to be ground. That's the black lead. I've hooked this up using a pair of double-headed pins to channel 1 of the oscilloscope. So the orange wire, which is the positive wire for the oscilloscope, goes to the yellow wire, which is the positive wire for the function generator. The orange and white wire, which is the negative wire for channel 1, goes to the black wire, which is ground. And you do need to hook both of those up because the oscilloscope's differential input, both inputs of the oscilloscope always have to be hooked up. It doesn't assume one of them is ground. That's different from some other oscilloscopes on the market, which are single-ended ones, and the other side of the oscilloscope is always ground. Here, it's a differential input. Both of them need to be hooked up. Okay, so let's take a look at what that looks like in waveforms. What I've done here is I've selected the WaveGen channel. Maybe I should hide that and show you where you get it from. And this is set up not with the default settings, because I was playing with this a little bit earlier, but with reasonable settings. So I've set this up as simple. That is the default. There are other choices here, basic, custom, and so on. We don't need them for this class. If you wanted to draw a really arbitrary waveform generator, use the custom one. Maybe we'll look at that a little bit. Sweep and modulation allow changing the frequency or changing the amplitude while you're playing the output. We don't need that for this class, but they're useful for some other applications. Simple is probably all you'll need. You then have a choice of several different built-in waveforms. And that's really the difference between simple and custom, is that for custom you build your own wavetable. For simple you use one of the built-in ones. The simplest one is just DC. There is no wavetable. You're just doing the offset. And indeed you can see that frequency, period, and amplitude have all been grayed out, and all we've got is offset. Quite often we'll be doing a sine wave. There we can specify the frequency or the period. We only get to specify one of these. If we specify the frequency, then the period gets set automatically. Similarly, if we set the period, then the frequency gets set automatically. And you can either do it with these pull-down menus under the arrows, or you can just type in a number. I want 2 point, and you can get quite arbitrary frequencies and periods. The amplitude is how big the signal is. Here I've got it set to 2 volts. I could set it to 500 millivolts. And now you can see it's showing you what the waveform looks like. Here it's going up to 0.5 volt and down to -0.5 volt, which is a little hard to see because it's behind my head. But you can see on this axis over here. The offset is added to that, so if I added 1 volt to there, now you notice it's going between 1.5 volts at the high end and half a volt at the low end. The symmetry here, we generally don't play with that for sine waves. Phase, we're usually not interested in that, but we can change that to be 90 degrees, and you can see that it's changed the phase of the waveform so that we're starting now 90 degrees way in, so sine 90 degrees is +1, rather than starting at sine of 0 is 0. Again, that's not something we need to play with very often when we're doing a single channel. Sometimes when we're doing 2 channels and we want them to be in a fixed phase relationship to each other, then it does matter. If we're doing that, we would want to turn on synchronization between the channels. Here, because we're only using 1 channel, synchronization between the channels doesn't matter. So I will set this back to 0. All right, let's take a look at what this looks like with the oscilloscope. So I'm going to go up to the plus sign here and turn on the scope. And we're not running at the moment. If I turn on run, I'm not seeing anything because the wavegen isn't running. Clicking on the green arrow turns on the wavegen. Now, this is flickering a lot back up here, and that's because it's got auto triggering on. And it's triggering on channel 1, but it's triggering on channel 1 rising through 0 volts, and channel 1 never gets down to 0 volts. Here we had 1 volt plus or minus a half a volt. So if I change that from triggering at 0 volts to triggering at 1 volt, now I can see the waveform quite steadily, and you can see that the period is about 2.2 milliseconds, something like that. If we go back to looking at what it's supposed to be, wavegen said it's supposed to be 2.115 milliseconds. It looks like it's doing the right thing there. Okay, let's take a look at some of the other wave shapes we've got here. A square wave, that's just going to go between the high voltage and the low voltage. If we go back to looking at the scope, sure enough, that's what it's doing. If we look at triangle waves, that goes between the top and the bottom, but now it's ramping up and ramping down for those two. And sure enough, we get a nice triangle wave. We've got symbol ramp up. This one just goes up and then starts over, goes up and starts over, and it's going from half a volt to 1.5 volts, and we look at that on the scope, and sure enough, that's what it's doing. Ramp down does the same thing but going down. Noise is kind of an interesting one. It's not a periodic waveform, it's not using a lookup table, it's doing a random function there where, well, let's take a look at it. It's got the same range as before, but it's Gaussian distributed random noise. Or actually, it's probably not Gaussian distributed, it's probably, it might be flat distribution. At any rate, it's white noise that's not periodic. Okay, pulse waveform is kind of interesting. It's like the square wave, but it doesn't go down to the negative half. It just goes between 0 and 1 in the 2 labels. So this is now the amplitude, the half plus a half volt, and this still has the offset added, but it doesn't go the half volt below. So it's 0 and 1 times the amplitude rather than -1 to 1 times the amplitude. And if we look at that, sure enough, we've got something that's just pulsing. That's sometimes useful when you want to make something that looks like a digital signal, because digital signals are usually between 0 and a positive voltage. And the trapezium and sine power we basically don't have any use for in this course. So that's probably all you really need to know about the function generators for this class. One important constraint here is that we can't go up to really high frequencies. If we go up to 5 megahertz, look on the scope. Oh, we're going to have to change our time base here now to see that. Okay, we can do a 5 megahertz signal here without too much problems, but we can't get above about 10 megahertz. And This signal here, though it looks nice and smooth, we're sampling it at 100 megahertz. And so we are going to have, particularly at the very high frequencies, some limitations on what frequencies we can get and some artifacts if we're not picking something that divides evenly into 100 megahertz. Okay, that's probably enough for now. We'll talk more about the analog discovery 2 in subsequent videos.